So recording had started. So good afternoon and welcome back to the session for graph neural network. Um, previous session was an important session in which we have discussed about the embedding. Okay, so and I think most of you have not attended the session. So I request all of you who have not attended it to please go through the recording and then move forward. Okay, because that session was an important session, and Professor Vipin has defined, or we can say clarified, the concept of embedding, node embedding, and graph embedding. I think graph embedding he had not covered. Graph embedding he'll be covering later on. I think he had focused more on the node embedding part. Okay. He had explained a bit about graph embedding, but not in full detail. If you do remember, can anybody confirm? Is anybody who has gone through the recording and can confirm to what extent he had covered the graph embedding? Because as per me, I think he had just given a brief concept, but not covered in full detail. Node embedding, okay, but not graph embedding. He had given a brief introduction only. Okay, although this question was not appropriate because I was also a part of that session. Okay, still I'm asking you, so that's okay, fine. So not the classification. I'll have to cover the neural message passing first, and then we'll move towards the graph classification. Okay, so today we'll be starting with the GNN, and I think I have explained you full detail about the latent variable. Okay, latent variable and latent space. Uh, do you remember? I think this we have discussed in the 8th context session just before midsem. I have enabled the mic. Oh, sorry. Is it good now?
Yes, sir.
Okay, chalo. Okay. Can I further reduce the size of this window? Can I do that? I don't think I can. So I can minimize it. Okay, fine. I'll come back to those videos. Not video. Uh, frequently come back to that screen. Okay. So just quick overview what we have covered in the 8th context session, because 9th was not taken by me. It was taken by Professor Vipin, and he had explained the embedding part. And we'll be starting up with the GNN, graph neural network. Okay, now, so there are some key terms, multi-layer perceptrons and permutation invariant and equivalence. Okay, fine, I think. And the topic that we were about to cover, but I think I was not able to cover in full detail, was the neural message passing. Okay, so the moment we talk about multi-layer perceptron, and in graph, it is by default, but not by default, it can easily be implemented and can take care of the network, or we can say neighborhood, while creating the perceptron, all those layers of message passing. So what those layers, or we can say how those layers can be defined, layers can be defined based on the neighborhood. So for example, I think if our target node is A, on the first layer, we will be having all the neighbors of that target node. So neighbors of target node are here are B, C, and D. Okay, so this is layer 1. And those are direct neighbors, one hop neighbors. Okay, and they send their messages to A somehow, and those messages are aggregated and updated in some sense, so that we have a black box which aggregates, which collects all the messages, and based on the all the messages sent by the neighborhood, they collect and update it, put it in one box. Okay, and then update it and update the message of A, whatever the value of A is, it has been updated. So the current value of A plus the data shared by the neighborhood is being aggregated. So A's value will be updated. Okay, now if I want to increase the layers, so layers at the second layer of the target A, what will be the second layer of perceptrons? So second layer of perceptrons will be the neighborhood of those nodes. So the first is B. Who all are the neighbors of B? Neighbors of B are A and C. Okay, so A and C, they themselves send their messages, and it has been aggregated in a black box. And based on the values of A and C, the B value will be updated, and updated value of B will participate in this aggregation and then update the value of A. Okay, same is the case. The second neighbor, which is C. So who all are the neighbors of C? Neighbors of C are A, B, E, and F. So A, B, E, and F, they will be in the second layer. Similarly, for the D, who all are the neighbors of D? There's only one node, which is A. So all those nodes will be at a layer 2. Okay. And who all are they? A, C, or who all are they? If I compile those nodes, they all are the second hop, 2-hop neighbors of A. So they are 1-hop neighbors. They are 2-hop neighbors of A. Okay. So that means if I pick, if I consider at the term of the node which are traversed. So in the 1-hop, if I take 1-hop neighbors, the node are these, and this. If I take 2-hop neighbors, so 2-hop neighbors will be this, and this. So that means the size of the neighborhood. The size of the neighborhood is increased when I increase the layers in perceptron. Means more and more nodes are participating for updating the value of my target node. Okay, it's not visualizable proper because this is a simple graph. If that would have been a bigger graph, suppose for example, this is my a bigger graph and this is my target node. Okay, so that means 1-hop neighbors will be a node with the direct edge. 2-hop neighbors will be those nodes which are neighbor of a neighbor. Some nodes will be repeated, fine, but they will be the neighbors of a neighbor. 3-hop neighbors will cover more part of a graph. Okay, the range of the nodes covered in a 3-hop neighbors means if I increase the third layer, there'll be few more nodes which were not in this graph. All the nodes were traversed, but let us assume for a bigger graph, some nodes will be repeated. Some nodes of 1-hop neighbor, layer 1, some nodes of layer 2 will be repeated, but there will be many neighbors. There'll be many nodes which were not repeated. They are introduced, or they are newly introduced into the coverage. Okay, so if I increase the hop, the size of the neighborhood participating in updation of a value of node A will be more. So ultimately, what is the physical interpretation? Physical interpretation is the value of A is being updated based on major portion of a graph. Okay, they all participate in updating the value of the target. So that means if more and more nodes are being participating in updating a target node, so that means it may be a more accurate or more information is being processed. Okay, and we will be doing it for all the nodes of a graph. So that means more and more information will be processed while updating those values, those values of each node of a graph. Okay.
Sir, sir,
G.
one question.
Ha.
So here in the previous slide, if you see, A is its own two-hop neighbor.
Mm-hmm.
Can a node be its own neighbor? Well,
Yeah.
it could be n-hop.
Ha. It can be possible.
Okay, then one hop is should also be possible, sir. Can A be its own one hop neighbor? We don't take that, right?
A one hop neighbor if there is a self loop.
Sorry, there is a.
If there is a self loop,
Acha, okay.
if there is a loop, means if there is self loop, then in that case, A is also a neighbor of A.
Okay, got it, sir. Thank you.
But most of the time, we prefer. अरे यार, अच्छा इसके साथ एक प्रॉब्लम रहेगा टास्क बार के साथ. But normally we avoid the nodes or the graph with self loop and parallel edges. Okay, so we avoid the self loops and the parallel edges. Parallel edges means like this: there are two edges pointing to the same node, so we avoid them most of the cases.
Okay, so more likely A could also be present in third hop and fourth hop and so on also.
Maybe possible.
Okay.
Suppose, for example, A and F are two hop neighbors. Okay, it may be possible that this edge also exists. So F is also one hop neighbor as well as A and F are one hop neighbors as well as A and F are two hop neighbors as well. It may be possible G, H. Okay, there's an H between A and H. So 1, 2, 3. So A and H are one hop neighbor as well as A and H are three hop neighbors as well. So it may be possible.
Okay, thank you.
Okay, but the concept which I intend to explain in this, if I increase the hop, then there's a major portion of a graph. If I increase the size of the hop, we can say hop neighborhood. If I increase the number of hops, then more and more nodes will participate in updating my target node. Means major portion of a graph will participate in this updation. There will be a drawback also. The drawback will be as I increase the layers, the computation will increase because as per the power law, I think I have explained you the power law. There will be some nodes which have a very high degree. Okay, so that means if a node has a very high degree, means its neighborhood sizes very much. Okay, so in that case, the computational capability will not capability, computational complexity will be increased. So simple CPU may not work well, and in that case we may require GPU or parallel processing to get the work done. Okay, so me and Professor Vipin, basically Professor Vipin was working on a problem in which we were trying to identify the subgraph. So it's like subgraph mining, and there we encounter a strange scenario when even when we increase the hop, even for one hop, it was taking around few hours. But when we increase the hop neighborhood just one to from one to two, the program crashes. Okay, because the neighborhood size becomes very huge. So the program was not able to, the program memory was not able to accommodate that, and it crashed down. So even with the increase in one hop, our concept was not working. Yeah, Avinash. Sorry, Avnish.
Sir, in that case, what is the solution? I mean, should we sample out or, I
Ah,
mean, okay,
in that case, we need not to take all the neighbors. We'll take the partial neighborhood, okay, or we take a sample. Sample aggregation may be the best option.
okay,
Or the method that we use is we ignore the second hop neighbors. We just continue to work on one hop neighbors only.
okay, but that may degrade the performance overall.
But not that much,
Okay,
because our in that case, if you if your main concern is the size of the neighborhood, then I think it will degrade. Okay, but for our case, we were talking about subgraph mining. So even for one hop, it was giving a comparatively good result. But based on the situation, we'll have to change the logic.
okay, sir, thank you.
Okay, so the model aggregate the message from A. Okay, now I think all those where that is it. Why is it not working? Now it is. Sorry. So now I think we have, as we have talked a lot, I can go through those. Many of those PPDs are simply covered. Okay, I can simply go through them, and they are self-explanatory. So the model aggregate the message from A's local graph neighborhood BCD, and in terms message coming from these neighbors are based on the information aggregated from their respective neighborhood, which means that B is updating its message from A and C, and A is updating based on the neighborhood of B, C, and D. So this visualize show the two layers version of the message passing, and this is an iterative process. If I means A and C will update the value of B, B will update the value of A. Okay, now this is for one node. When my target node is B, I will be using the updated value of A now, and rest of this updated value of A will update the their own neighborhood. So if suppose, for example, for one iteration, we have updated the value of A. Now, if my second target node is B, if I work, if I'm done with B, if I'm done with A, now am I, if I'm working with B, then if I'm using the updated value of A, then this updated value of A will affect the will give me a new value of B, as well as new value for C, as well as new value for D. Okay, and so on. In respect, then when C is updated, then again C will again update the value of A, B, E, and F, and so on. So that's why this is an iterative process. Once it is updated, it will affect the another one. So notice the computational graph of GNN forms a tree structure by unfolding the neighborhood around the target node. I think the this statement is talking about this one, because this will be something like a tree structure, but in a reverse order. Tree by default, tree means root node and then to their target and then to their children child nodes. Okay, but here the flow of information is reversed from child node to towards the root node. So flow is from leaf to root. That is the only difference. But the structure is tree structure. And during each message passing iteration, a hidden embedding HUK. So this K is not the power, this is the iteration, because as it is mentioned that it is an iterative process. Okay, so we will be doing it for respective iteration, first iteration, second iteration, and so on. So this K is a iteration. So we will be updating the value of the next iteration using the previous iterative values. Okay, so using the previous values, we are updating the value for the next iteration. So this power, or no, not power, this superscript is not the power. This superscript is the iteration. Is not power function. It is iteration. Okay, so please do not confuse this as HU to the power K minus 1. No, it is kth iteration. Using the values of kth iteration, I am getting the value for K plus 1th iteration. So a hidden embedding HUK correspond to each node. So correspond to each node, the embedding value is being updated. So is updated according to the information aggregated from the neighborhood. Okay, so what does this mean? The statement is aggregation function. So there are it can be considered in two part. Okay, this update function is of two part. First, value from the neighborhood is being aggregated, means clubbed, combined, or collected. So this means this HV for the kth iteration for all V that belongs to the NU, where N is the neighborhood. Okay, so U is my node. Suppose, for example, if U is equals to A, then what will be the NU? What will be the neighborhood of A? Neighborhood of A will be the node which are in neighbor. So that means BCD. So neighborhood will be B, C, and D. Okay, so this will be for all. Now, so the value is being aggregated or clubbed, not clubbed, aggregated or collected from all the neighbors. So this all the values from means the values from B, C, and D are being collected into one box at one place. So aggregate kth iteration HVK for all V that belongs to the neighborhood. So this is the meaning behind this expression. So values from all the neighborhood are being collected at one place in one function. This function can be a summation function. I can add all those values. It can be a multiplication function also. I can multiply with all those values, whatever the value which I have received. Okay, but somehow I have compiled, I have collected all the values from the neighborhood. Okay, so this is what. So, and it's in initial value HUK. What does HUK mean? Suppose, for example, like a page rank. Okay, so suppose initially the page rank was 1 by n. Okay, initially the page rank was 1 by n. Then based on the neighborhood will have their own updated value. So based on the neighborhood, the page rank value was updated. Okay, so somehow it has been collected. So initial value, its own initial value, plus whatever the value collected from the neighborhood. Based on that, somehow this value is being updated. Means that node embedding for the next iteration is updated based on some function of its, some part of its initial value, plus some information from the neighborhood. So that we call it as this function. So our update function, current value, and its neighborhood value. Message. So update and aggregate are arbitrarily differential functions. They are in MNU is the message that is being aggregated from the neighborhood. Okay, so I hope this expression is clear. So its own updated value and some value from the neighborhood is also added, and both the values are somehow computed. Okay, so its own initial value or its own original value plus the information from the based on the neighborhood, somehow they have been mixed together. Suppose for example 20% of neighborhood is being accommodated, so original value plus 20% of neighborhood is being updated, and that updated value will be the node embedding for the next iteration. Okay, and this is done for all the nodes, for all nodes of a graph. Okay, if you can resemble this with the page rank computation, then I think it will be easy for you to visualize. Everyone will have their own initial values, then based on the neighborhood, the values are being updated, and then step by step we do it for all the nodes of a graph. Then the page rank for the whole graph is being updated, and that is for iteration t. Now that value is being used for computing the next iteration value, which is for t plus 1. Okay, so I hope that's clear. Is the visualization clear to you all? Could you please shed light on the difference between the option B and C here? What is it? अरे यार ठीक है. I think this is related to that quiz, and I think we have already discussed it into the session. Okay, uh, I'll definitely talk about it, but later towards the end of the session. So please stay back. We'll discuss it. Hardly it will require 2 minutes. But as of now, I just want to break the flow. Is it good? Are you able to visualize this update method and aggregation one? Please confirm. Okay, take care. So at each iteration k of GNN, the aggregate function takes as an input the set of embedding of a node in US graph neighborhood and NU and generate a message MNU of the case iteration based on the aggregated neighborhood information. The update functions combine the message which he had received for that iteration with the previous embedding of the same node. Of the node U, because I'm currently working on the node U. So the message from the neighborhood as well as its own previous value would generate the updated embedding for the next iteration. Okay. The initial embedding at k equals to 0. Now the question arises, what should be my initial value? Okay, so initial value problem. So what should be my initial value? In the page rank, what was the initial value? The page rank was 1 by n. Here in this case, at the initial embedding, at the initial iteration, what can I use? I can use the input features of all the nodes. Or in the best case, if none of the feature are available, the adjacency matrix can also be the default one. Or if there are some attributes associated with each node, then those initial set of attributes will be my initial node embedding at the kth or at the 0th iteration. So HU0 will be XU for all the U's of the vertex set of that graph. Okay, so initial node features will be my initial node embedding. And after executing it for k iteration, so after running k iteration of a GNN message passing, we can use the input of the final layer to define the embedding of each node. Okay, so that we call it as ZU, latent space, or we can say latent embedding or embedding. So ZU will be HU for the kth iteration for all the nodes of the graph. So since the aggregate functions take this set as an input, GNN defined in this way are permutation equivalent by design. Okay, because I'm taking care of all the neighborhood. Okay, so that's why in this way I have converted it used in I have converted into a permutation equivalent. Okay, if I'm taking care of all the neighborhood, so A first and then B and then C, or C then B then A, it doesn't matter because I'm summing all the values. I'm aggregating all the values. Either I'm summing it or I'm multiplying it. Okay, either I'm taking a sum or a product of all. So either A plus B or B plus A, it doesn't matter. A into B and B into B into A, it doesn't matter. So that's why we have converted, we have get rid of that problem of permutation in invariance. So this method is permutation equivalent by design. GNN framework requires that we have a node features XU for all V's as an input of model. Okay, in many graph, which we have a rich features, we use that Zine expression features for biological network, text features in a social network. So we have various methods by which we can have those features associated with each node. When there is no node features available, for example, there is the we are not all those features are not available, or they're not useful to us. So what we can do, if they're not useful to us, or they're not accessible to us or known to us, what we can do, we can use any or some of the network measures that we have learned so far. Okay, so that's why we have devoted sufficient time in finding out those numerical values out of the graph. Okay, they can also be used, or they can be used in addition to the node features as well. Some combinations of node features plus network measures. The combination can also be used for the embedding. Okay, depends upon the requirement. So what is the benefit of message passing? It works on the original graph structures and no pre-processing is required. We just need the neighborhood. Graph in practice are typically sparse. Sparse means the number of edges are far more lesser than the square of the vertices, means the number of edges are less as comparison to number of nodes, but that graph is still connected. Okay, so for example, if my graph is of 10 nodes, so that E is very much smaller than 100. It can be 50, it can be 70, it can be 45 or something. So this is the definition of writing a sparse graph, where E is very much lesser than a square of the number of vertices. And thus MPGNN is able to scale to a very large but sparse graph. So we are able to do that. And each of the three operations, message, passing, okay, communication through that, aggregating it, collecting all the messages from the neighborhood, and updating the information collected from the neighborhood, can be computed in parallel across all the node. Okay, because I'm not using the latest updated value. Okay, for the kth iteration, I'm using only the k minus 1th iteration values. Although I know that, or we all know that, if we use the latest updated value, then the convergence will be faster, but it will arise into some problem of deadlock and consistency and coherency. Okay, so those issues of message passing interface, MPI, will comes into play, those semaphores and all. So I'm not, so in order to avoid it, because we'll have to we will have to take care of those cases, especially that consistency, coherency, and I think there was one more C. If you do remember, what was the three C's in message passing, MPI in interface? MPI means interface, message passing interface: consistency, coherency, and concurrency. Okay, because at that time we will be updating the real time values. So in order to avoid it, better use the previous iteration value for all the next iteration value. So if we can do that, then we can implement this in parallel across all the nodes of a graph. So that's why for GPU is far more better in case for the computations, because we can do it in parallel, in even the parallel processing. And edges which is beneficial for parallel computing platforms such as GPU or MapReduce system. Because it is a natural and easy to be implemented in practice, most GNN architecture essentially follows the MP-GNN framework by adopting specific message, aggregate, and update operations. And most of the time, it is summation or some kind of multiplication. But simple one. So the basic intuition behind the GNN message passing framework is straightforward. For each iteration, every node aggregate the information from its local neighborhood only. For one hop, direct neighbors. For two hop, neighbors of a neighbors. If I increase the hop, then the more information from the we can say graph coverage will be more, but on the cost of computation. But still, if we can still parallelize it, we can still use it. So as this iteration progresses, each node embedding contains more and more information from further reaches of the graph, from the distant part of a graph. So what are the motivations and intuitions? So kind of information a node embedding actually encodes structural information about the graph. For after kth iteration of a GNN message passing, the embedding HU for the K of node U might encode the information about the degree of all the node in U's K hop neighborhood. Okay, so when analyzing the molecular graph, we can use the degree information to infer the atom types and different structural motifs, such as whatever the such as it is a benzene ring, or we have a hydroxyl bond or single bond, double bond, and many other things. The second is the feature based information about the graph. So after the kth iteration of a GNN message passing, the embedding for each node also encode the information about all the features in the K hop neighborhood. So this local feature aggregate the behavior of GNN is analogous to the behavior of convolution kernels in CNN. It's almost a similar. However, whereas CNN aggregates the feature information from specially defined patches in an images, GNN aggregate the information based on the local graph neighborhood. Okay, and here the structure is well defined. So the basic GNN message passing, it can be defined in that form. So GNN framework discussed so far was in relatively abstract fashion and a series of message passing iteration using update and aggregate function defined above. So in order to translate the abstract GNN framework into something we can interpret, we must give concrete equation to this update and aggregate function, and this is how it is well defined. I'll explain you all. Again, I repeat, this superscript is not the power. The superscript is the iteration. So using the kth iteration values, k minus 1th iteration value, we will be finding out the value at the kth iteration for each node. And this is for the embedding. Okay. So HU means embedding of node U. For the kth iteration is updated by some sigma, some function, self. Okay. So this again is a weighted graph. Self embedding of that node plus weighted matrix for the neighborhood. Okay, to what extent we want to give to the to what sort of neighbors. Collection of embedding from all the neighborhood V belongs to NU, HV K minus 1. So for the previous iteration, okay, plus the biased term. Okay. So biased term means we just if you do remember what is the purpose of the biased term? To in the worst case, the biased term is some positive value, just to ensure in the worst case, if this value becomes 0, then we'll have something non-zero value. So just to make it something positive, we use the bias term. Okay, I think if you do remember where we have used the bias term for the first time, in which network measure, if you do remember, it was in the after the eigenvectors, after the eigenvalue centrality, third centrality. Okay, so the basic idea of this bias term is same, some positive value, just to make sure that if everything becomes 0, in that case also the embedding should not be equals to 0. Embedding will be at least some positive value. Okay, but most of the time in all the research papers, this term is omitted. Okay, so that's why the term BK, that is a real number, a small real number, is often omitted for notion simplicity, but including the bias term can be important to achieve a strong performance. Okay. And in that case, the bias value allows to shift the activation function to the left or to right, which may be critical successful learning. And you can say the bias makes the equation more flexible to adopt the best values as to keep it non-zero. Okay. W self, W neighbors, they are the trainable parameters, matrices. This is the activation function. Most of the time, we'll use ReLU, 10H, or sigmoid function. Okay. So we first sum the message incoming from the neighbors. So the method for update is sum. Aggregation is the sum. So aggregation and update. So we first sum the message incoming from all the neighbors. So aggregation. We combine the neighborhood information with the node's previous embedding using linear combination. Okay, so this is the update. This is the aggregate. Okay, and this is the update function. Some linear combinations of both. The previous one, the previous embedding plus the value from the neighborhood. Okay, and then after doing it, so this is what is explained in 1 and 2. So this is step number 1. And this is step number 2. And then finally, we applied some kind of element-wise non-linearity. We use ReLU or the 10H or sigmoid function. Okay, why it has to be non-linear? So what is the effect if I still make it, why I want to make it non-linear? Why not linear one? So it is explained in this way. So without the non-linear activation, suppose we did not use the non-linear activation function, we use any activation function. A neural network, no matter how many layers it have, would behave just like a single layer perceptron, because summing all these values would give us just the another linear function. Okay, so layer 1, layer 2, layer 3, no matter if how many layers will be, it again will be a combination of a linear values only. So that just to get rid of, and it will lead to a premature convergence. And I think in this way we call it as over smoothing. Okay, just to get rid of it, we use the nonlinear. And in another way, it means that output cannot be reproduced from a linear combinations of an input, which is not the same as output that renders to the straight line. The word is from the word is from the affine one. Okay, so it cannot be regenerated back. So the formula, or we can say that the whole expression of GNN is written in this way. So we can equivalently define the basic GNN through the update and aggregate function. So message from the neighborhood will be the embedding collected from all the neighborhood. The update function requires the self-embedding, the embedding of that node by himself, plus, in addition, not plus, with the message from the neighborhood. Okay, so some form of some learnable parameters for self and from the neighborhood. And this is the aggregate function. Okay, they are can be shared across the GNN message passing or can be trained separately for the each layers. Okay, fine. Okay, it will be towards the last. So if I many GNN can also be succinctly defined using the graph level equation. If I write if I wish to write in the form of a graph level equation, then it will be in the form of matrix. So H is my matrix for certain iteration. So here HK is a set of those real numbers of order V cross D. So denotes the matrix of the node representation at a layer T, means layer T means iteration T in a GNN. It will be some linear function, so adjacency matrix from the neighborhood, from the self. Oh, in that case, self was the first part and the neighborhood was the self part. In this case, it should have written HK minus 1, this part first and this part to the second. So self I'm embedding plus the embedding from the neighborhood. And A is my adjacency matrix. And the bias term is omitted for the notional simplicity. It's not the case that they are not being taken care of. If you will build up a model, you will have to include the bias term into your computation. It's not the case that if it is not mentioned, we can ignore it. It is not a factor to be ignored. It has to be there. But most of the research papers and in the book, throughout that book of GNN and many other research papers, they usually didn't write it. So it is assumed that it should be implemented by default. Okay, I think somebody has unmuted himself for some query. Harsh, please stay back. And is there any member from group 16? Is there a group 16 assignment group? Is any member present over here today? You can unmute yourself and say yes. Fine. ठीक है. Now the limitations of GNN. So message passing graph neural network iteratively update the representation of each node by aggregating the representation from its neighborhood. The obtained node representation essentially encode the subtree rooted for that at that node. Okay, so that means this will be, if I'm talking about the subtree, this is okay. This is a subtree. So this node embedding of A will also be will be depending upon the node embedding of C, which itself is a subtree rooted that node. Okay, so C will have their own embedding method. Okay, so C will have the same method as of A, even if it is for layer 3. If I'm talking about B will have their own step, means that will be repeated iteratively. Okay, the same pattern is repeated iteratively over each layer. However, using this rooted subtree to represent a node may lose some useful information, such as information about the distance between multiple node is lost. Okay, what does it mean? It means that how far is A from C is. A and C is at one hop neighbor. Okay, how far A and F are in the graph. A and F are at the two hop distance. Okay, if that would have been some more node, A and U will be two hop distance. A and A and V will be at three hop distance from each other. Okay, fine. In the graph, this thing can be calculated. Okay, this is visible, but are we taking care of this information, this distance between two nodes into account while aggregating the information, while aggregating the embedding? No. Okay. So how far they are, how close they are, I'm not taking care of that distance. Okay. Huh. If I still want to do that, I can implement this in terms of, not exactly I can do that. If I can use the weighted method, some form of weighted method. So for example, if there are suppose four layers, so I 40% to put 40% weightage is given to the embedding of these one hop neighbors, then 20% weightage is given to the embedding of um, uh, three sorry, one hop neighbor, two hop neighbors, three hop neighbors, and four hop neighbors. We can do that, but it will be difficult for us if we are implementing this in parallel, because B is computed separately, C is computed separately, D is computed separately, and wherever the C is computing, the process, the thread where C is being computed, it again parallelize it in the form of four different parallel threads. Okay, so if we want to include that weightage also, it is difficult. It is not that easy. Huh? We can do that if it is in a sequential manner. If in a form of a parallelization, this will be difficult. So weighted distance, or we can say, but still in that case, we are not including the distance value into the into the computation of node. We are just assigning a weightage of layers. Okay, so that is one limitation. So information about the distance between multiple node is lost. We are not ever we are not we are not taking care of this value ever in this computation. Second is the information about the cycles is lost. Okay, so although because of the cycles the nodes are repeating itself, okay, but not only because of the node, there's one more factor of pendant vertex. So especially in case if I say, okay, suppose B is repeating again, so A to C, A to B, then B to C, and then C to A. Suppose for example, A, C, A. Is it a cycle? A, C, and then A means no. So in that case, for B, A, B, C is a cycle. So in that case, A, B, and then C, when I take care of C, then again it will be A, B, C. So somehow cycle will play its role in deciding the neighbors, but specifically the information about those cycles to of distance 2 or not distance 2. A minimum cycle will be of distance 3. Okay, so 3, 4, 5, and 6, or whatever the size is not even being computed or taken care of. Even those pendant vertex Because of those pendant vertices also, the node will repeat itself in the computation. Okay, so loops or cycles are not being are not being we can say the information about the loops and cycles are not being taken care of or are not being computed in this way. So this is the second limitations. Okay, I've already discussed it. Now, what is the impact? Okay, why do we really want a distance to be taken care of? So MPGNN has a limited power of capturing the position or location on a given graph in a given node with respect to the another node in a graph. So many node may share similar subtree, and thus MPGNN produces the same representation for them, although the node may have located at a different location in a graph. So for example, this one. So this location of a node is crucial for the task that depends upon the multiple nodes, such as the link prediction. As the two nodes that tends to be connected with the link are typically located close to each other. So for example, I've taken this example from this research paper. There, there were two different trees, the we can say food chain tree. Okay, so this is for the land animal and this is for the aquatic animal. Okay, so these are two different species, but fortunately or unfortunately, the structure of the graph is same. Okay, now if this is the case, then there are two scenarios. If suppose in the original graph this edge is missing for the aquatic animal, but it was there in the land animal close graph. So should that edge be there or not? Okay, and the second is, if this is the case, which one is more likely a predator of a pelagic fish, Lyrex, or an orca? Okay, who can be the more likelihood? We can say who can be the predator of whom? Okay, so this may be difficult to answer. The food web network example that demonstrate the limitation of a GNN. So MP GNN will associate the Linux or and Orca with the same node representation. So node embedding will be the same as these two nodes hold the same rooted subtree. Okay, we are not taking care of the node features. The only thing is we are talking about the structural or we can say structural properties of a graph. Okay, although this is a land animals and these are the aquatic animals, so node features are not being considered. If I'm bothered on only about the structural information, then in that case it will be difficult. So the message passing GNN cannot predict whether Linux or Orca is more likely to be a predictor of this fish, means link prediction is not possible. Even if the structure of both the graph looks same, if I'm not including the node features in the case. So in this case, the MP-GNN fails. Fails to predict link prediction or recommendation, something like this. So if This is the one example. You can generate many other use cases based on the structural. The second, information about the cycles is lost. Lose track of the node identities. Okay. So why that cycles are important? What will be the difficulty if we face if we are not able to track the cycles into the graph? When we are talking about the subgraph matching and counting, because loops frequently appears in a queried subgraph pattern of a subgraph matching or a counting problem. So it was formally proven that GNN is able to count the star network, particularly in the form of a trees, but cannot count the connected subgraph with the 3 or more nodes in the cycles. So it was proven initially. Now, the second example, okay, why that tree, what type of information which is lost. So for example, if there are two graphs, G1 and G2, okay, in this case, my target node is U, and in this case, my target node is V. They both are different graphs, but when I'm trying to draw the message passing layers for 2-hop, both the graphs, both the embedding tree will be almost the same, although the initial graphs are not same. So the node representation of HV and HU is same, given by the MP-GNN, which are same. So, but although they belongs to the different cycles, this belongs to the 3 cycle and this belongs to the 6 cycle respectively. So that means the information about the cycles cannot be covered in this case, cannot be taken care of, because based on this, if this is my scenario, both of them will give me the same embedding tree. Subtree will be the same. Then the third is the scaling. So there are two major challenges while scaling the original implementation of a GNN to a large graph. First, most of the GNN model usually compute the entire adjacency matrix and node embedding of the graph, which demands huge memory space. Because we'll have to do it for every node of a graph. The embedding is calculated for the every node of a graph, okay, and it takes care of the neighborhood. If my hop size is more, then more computational will be used. Computational complexity, we can say, computation power will be used if I increase the size of the neighborhood. Okay, so second is the scaling issue. The second is training GNN requires recursively updating the gradient for each node in a graph. Okay, and that too, this has to be recursively updated. So this becomes infeasible and ineffective for the large graph. So the gradient descent may take too long to converge on a large data set. So in that case, a stochastic gradient was introduced to speed up the process towards an optimum. So in that case, in spite of gradient descent, stochastic means what is the stochastic means? Not to do it for all, do it for some only. Stochastic means probabilistic. Probabilistic means randomly. So not to all, just for some set. Are we not considering the node features for GNN generating the node embedding? Yes, we will be, because they are the feature vectors. So that's why they are called as feature vectors. We will be. But as of now, I'm just starting it up. So in that example, if we are not including those node features, that problem was arising. If I think if your question is regarding that lyrics and or का example ना, Upendra, is it correct? हाँ हाँ, for the limitation. So definitely, मतलब, but this was for the example कि if we are not taking care of the node features, if we are deciding based on the structural or the connectivity structural information only, then it will be difficult. So we will have to include the node features to take care of such scenarios. Okay. I cannot see the time if it's a screen. I cannot see the time. I'll have to come out and see the time. So please let me know. 2:47. We have started at 1:40. Yeah, we have sufficient time. We have full 1 hour. ठीक है, मैं बिना बात में डर गया. Okay. A lot more to cover. So please let me know, because if I ये क्यों नहीं जा रहा है? नहीं. हाँ, अब गया. Sorry. Uh, Previously I was using the Teams for the Chrome. Today I thought of using the Teams app in spite of the Chrome. So I'm not that familiar enough with that activity. Okay, fine. Currently, studies propose to tackle this obstruction mainly from the sampling paradigm. So how can we deal with this sampling issue, scaling issues? By taking samples. Okay, we need not to do for the whole. We need not to compute it for the whole graph. We'll be doing it for the part of a graph, sample of a graph, which we'll cover later on. Now, so till now we were having the three formulas for GNN, MP-GNN. First one, from the neighborhood.
तुम्ही सुद्धा एडिशनचे खाऊन बोर झालाय, मग चला तुम्हाला सुद्धा चटकन आणि पटकन होणार लगेचच अगदी पौष्टिक असं शिवाय तोंडाला चव आणणारं काहीतरी खायचंय. मग त्यासाठी एक कांदा घ्यायचा आणि
Savita, any query? Okay. ठीक है. Partially, I can understand Marathi, but not fully. When you will speak in full fluence, full speed, I won't be able to understand that. But if you'll speak slowly, I can, because I have been in that area for around 7-8 years. Okay, nothing related to this topic. Okay, so the first one, the message has been aggregated from the neighborhood. Then MNU, why we have okay. The second is we update the neighborhood value with the self values. Like this has to be in the second one. This has to be first, this has to be second, and this has to be third. Okay, so message from the neighborhood that all the information from the neighborhood need to be collected, and then it has to be updated based on the current node embedding value. Now, if we want to simplify this method and add the neural message passing approach, we can use the self loop to the input. And in that case, if I wish to include the self loop and omit the explicit update case, what should be the formula? So in that case, the formula will be something like this, where now in that case, embedding for the previous iteration for all the nodes of U. So if I'm working for node U, for all the neighbors of U, the embedding is being computed, and in that neighborhood, so this is one statement, for all V that belongs to NU and that node itself. Okay, so that means while computing for the neighborhood, the computation for that node itself is also included in the into the process. Okay, so for all V that belongs to NU union that node itself, this is one set. Okay, for this set, the embedding of the previous is being aggregated. So in that case, what is the advantage? The advantage is that the intermediate steps is being removed. So that node itself is being included into the set of neighbors. So by which it can be computed in the same way. So while computing for the neighbors, that node is also included. So that node is also included into that computation. So in that case, it becomes a one-step process. So it is equivalent to the sharing the parameters between W self and W neighborhood matrix, which gives the following graph level update, and we will call it as a self loop GNN in the form of matrix. How to include that node by itself? So A adjacency matrix plus I. Okay, so A plus I matrix for the node embedding value, node embedding matrix for the previous iterations into WT, the learnable parameters. Collectively, some nonlinear function. So what is the benefit for this? We no longer need to define an explicit update function. We can do it in a same method. So this is, we can often elevate the overfitting, but it has some shortcoming as well. It is also severely limit that expressivity of GNN. As now, what is the problem in this case? If we are computing about the node at the time itself, okay, so what is the specific information coming from that node is not being recorded, because the value is being updated along with the neighborhood. So what was actually updated from the neighborhood and what was actually from that node is not recorded. In this case, as it was a multi-step process, so value for itself was known, value from the neighborhood was known, and how it was updated, it was also user defined. Now, as we have included the same node into the neighborhood, so exactly what was its own information and what information was collected from the neighborhood, we are not able to differentiate between them. So as the information coming from the node's neighbor cannot be differentiated from the information from the node itself, both of them are merged together. So we cannot specifically identify, oh, this was the information from the neighborhood, this was his own information, and this is how we have aggregated it. Okay, so 80% of self and 20% of neighborhood information is being added. Earlier it was easy for me, but in this case it's not. But the beneficial is, okay, We need not to have multiple function, and we can get rid of this overfitting issue. So the most basic neighborhood aggregation operation simply takes the sum of the neighborhood embedding. One issue with the approach is that it can be unstable and highly sensitive to the node degree. This may be so. This may be one issue. For instance, suppose a node U has 100 times more neighbors as of U prime. Okay, so a node U has 100 times more neighbors as the U prime. Then in that case, summation of all those V's belongs to the neighborhood means this value, okay, will be far more greater than U prime. Okay, because the size of neighborhood is much bigger. So its value will also be much bigger. Okay, if so, those super high values. So this drastic difference in magnitude can lead to the numerical instability as well as difficulties for the optimization, because there will be very few nodes, and this based on the power law. As you know, if I am working on a real graph, definitely power law will be there. And I think in your mid-sem exam, you might have answered that question. If there is a real graph, there will be a power law in it. And I think we have devoted enough time for the power law. Power law will be there in each and every activity. Even if I'm counting out the degree, in degree, out degree, triangles, participation, length, whatever it be. In every computation, power law will be there. And this is one scenario. One node can have 100 times more neighbors than the another one. So ultimately, what is the solution for this? So the solution to this problem is to simply normalize the aggregation operation based upon the degree of the node involved. And I think in the past also, I have focused, or I have tried to explain to you many times. Normalization is one of the best method to get rid of super fit individuals or a very high value. Just normalize it, put it in some different range. 0 to 1, whatever it be. Okay, get it divided by certain maximum value. So that means those superfit individual are being captured into the same. So that means means jinn ko botal mein pakadna. That difference will, the proportional difference will still be there. Okay, but it's effectively numerical. The modulus value will change. So the simplest approach is to just take an average rather than sum. So first value, the first method is, in spite of taking a sum, take an average, mean. Okay, mean is the balancing point. I think in your ISM course, whoever has taught it, whoever have taught you, the main thing was mean means the balancing point of the whole data. The another method is, so that's one, summation of all those normalized by NU, size of the neighborhood. The another method is take a symmetric normalization. Square root of their product of their individual neighbors. Okay, so that's the another method. So symmetric normalization means d square root of dA square root of D inverse. So takes into account both your number of neighbors and their own number of neighbors. So in this, the largest eigenvalue being 1, that ensures by the square root. There should be a in this way. One bracket is missing. So where it is, where it can be used. So for example, in a citation graph, and we have already talked about how the citation graph is being created. I start with a paper, all his references will be his citation. Okay, every node will have their own set of references, and that will be their own. Even this paper has been referred by someone else, so that will be his citations. Okay, so and this citation is a directed graph. This citation graph is a directed graph. Okay, outgoing edges will be those notes, those research papers whom you have referred, and your incoming edges will be those papers who has referred you. Okay, now in a citation graph, the information from a very high degree node. So for example, paper that are cited many times may not be very useful for inferring the community membership of a graph. Okay, since these papers can be cited thousands of times across a diverse subfield. So for example, there is a paper with the name Neural Message Passing for Quantum Chemistry. At that time, what was his citation count? It was 7,000. Now let me check. Sorry, I used the shortcut method I was not able to get the plus sign. Okay, what was the name of the paper? Neural Message Passing for Quantum Chemistry. Neural Message Passing for Jet Physics and Quantum Chemistry. Where it is? It was there. For quantum chemistry. This is a recommendation system. 11,851. So now this count has updated. I will update it. 11,851. Okay. This seems that, oh, this paper may be very good if I want to start with the neural message passing. GNN. If I want to start with GNN, this paper may be very good for you. It may gives you an intuition. Because all others are message passing neural network, 190 citations, message passing neural quantum state for homogeneous electron gas, 72, for high order path, 69. So the rest of them are not that much cited. But as you can see, the citation for this paper is very much. So based on this, you may get an intuition that, oh, this may be a very good paper. Even if I start reading this paper, I will get a complete idea of MPGNN. Fine, but it is not so. The moment you start, when you this paper is directly available, Gilmer. Okay, this paper is available on internet. You can download it and you can start reading it. Okay, initially it goes well. Okay, but till that point, after a certain point, you will feel lost because they talk nothing about message passing, or in your computer science, that will not be much helpful. Okay, so this is an example where the nodes with a very high value may not be that useful to you. Because why this paper got so many citations? Because it was one of the base papers who have introduced the concept of message passing in graph neural network. Okay, so that's why whenever even I will, if I will write a paper on GNN, I will also refer this paper because they introduce the concept of message passing in the neural network, although related to quantum chemistry, but they were one of the initial members who thought of this idea. That's why whenever you are saying something related to GNN, we knowingly or unknowingly we used to refer those papers because they were the pioneers in that area. Okay, how much time do I have? Yeah. Apologies. Next time I won't be able to. I won't be using this MS Team browser. 307 half an hour. ठीक है. Any questions before we move ahead? Hush, please be there because I think you have been asking this question, I think third or fourth times. So I'll answer your question. Because you have dropped me 2 mails, I think. But unfortunately, I was not able to answer you directly. Fine. Any questions regarding anything that we have covered so far? We started with around 40. Now we are left with 22. Do you need a break? Is the session becoming boring? Because I was continuously speaking for those 2 hours. Am I audible? Oh,
yes, sir, you're audible.
Okay, fine. Can we incorporate a distance-aware weighting scheme in GNN that favors the immediate neighbors at every hop? As an example, if node B, C, and D are neighbors in node A, they would retain the elevated weight even when encountered at the second or the third hop. Retain the weights. Can we? So Bhupendra has asked a good question. You can go through the. Okay, you can see my screen, so you can also read it. So he had asked, can we incorporate the distance-aware weighing scheme in GNN that favors the immediate neighbors at every hop? As an example, if node B and C are neighbors of node A, direct neighbors of node A, they would retain elevated weights even when encountered at the second hop or the third hop. As of now, because we the model that we have thought of or we have discussed so far, we did not degrade the or we did not have the weighted we can say weighted for formula for the higher hop neighbors. So as of now, we are not using this information. But I think Bhupen, is your questions regarding the same scenario where we have talked about 40% to the direct neighbors, then 20% for the second layers, then 20% or 10% to the layer 3 and so on. Is it in that sense? Because that was just an example which I have taken.
Yeah, it is similar to that only, but instead of that, if we can give the more weightage to the nearest neighbors, suppose B, C, D are the nearest neighbors, even they come into the hop three or four, right? They should get the more weightage to get the actual message passing for that particular, node.
But they have been taken care direct neighbors, they are already taken care at the level 1, na?
No,
Even if they
yeah,
are
yeah, but
coming at the second and third, they are already being taken care at the first layer.
yeah, but they are even again calculated for the second and third also, right? If they are the uh, in cycle actually, right? In hop
Matlab
3 and hop 4.
they will participate in computing the we can say the embedding for their respective root node that is rooted at that point. So they will
Yeah, but
participate.
yeah, but they will, but in hop 2 and 3, right? The weightage will reduce, right? So even they are
Nahin,
in immediate neighbor. Suppose if we are giving the weightage for first hop is 40%, second 30%, and then 20. I mean, we can have any mechanism there. As the hop account goes on, right? The weightage reduces, and the neighbors which are there, I mean, the nodes which are there in those hops will also be having reduced weightage, right? So, even though they are having the immediate neighbor of that particular node. So BCD, even they comes in hop 3 or 4, right? They will be having reduced weightage, right? Instead of that, if we can give them the more weightage, it's just because they are in cyclic order, they are getting less weightage.
nahin, in that case, if because that the idea that 40%, 20%, 10%, 5%, what I've given is was just my idea. Actually, the model doesn't include that detail, that doesn't include that weighted part. Okay, that was the idea given by me. Okay, if we want, we can take care of, and the example that you have suggested will be the shortcoming of that idea which I have given.
Yeah, I
The
mean,
question,
that should be the case actually. Yeah.
huh,
Ideally, that
but
should be the case.
fine, but matlab, so your question is the shortcoming of my idea which I have given.
Mhm. Yeah, that is
But huh,
above that. Yeah.
but normally, normally we doesn't include that detail, na? Where it was, I think
Yeah,
I missed it.
I'm not sure, I mean, that is included or not, but I mean, this is my suggestion actually. I mean, we should be having, because the immediate neighbor influences more
Ah,
instead of the farthest.
fine. So that's, but I think for immediate neighbor, those immediate neighbor have already given their contribution. Those immediate neighbor have given, matlab they've already given their contribution in this layer now. So even if they appear again, again in that suppose C, suppose E, F to C. Okay, even if they appear again in layer 3, and if I reduce the weightage, their primary focus or their main value is already been taken care of now.
Yeah, it is already taken care, but not in the second or third hop, right?
Not in, but because at that time they are not that important.
No, but that is the immediate neighbor only, right? I mean, that doesn't matter because they are the immediate neighbor. They will be influencing most to that the root node actually. Even they are far away, right? But still they have the most influenced uh, properties or features that will influence that root node. See,
Yeah, fine.
I mean, this is my understanding.
नहीं ठीक है, but मतलब again I'll say the same thing. I need to, because I think I'm not able to think in that manner, because I'm still thinking that as I've already taken them in the first layer because they were the direct neighbors, so they're already been in, matlab, as they were important, their aggregation value will be important for me.
Sir, I think if it have more number of layers,
Not in that iteration. Sorry, Rajat, not in the next iteration, in the same iteration itself. in the same iteration. So suppose A, B, C, D has already been included. Now B, C, D again appears at 3 or 4 hop distance away because of the network graph. The connectivity can be in anything. So those direct neighbors appears again in the in the subsequent layers. And if we have implemented that 40%, 20%, 10%, 5% weightage kind of a thing, then Bhupen says that it should not be, because they are, although they are appearing at the later stage, but they are again important to that node. I do agree. So in that case, if you're not agree with that, then we can remove the concept of that weightage one. So that means that 40%, 10%, 20%, we can remove it. Equal weightage, we are not even taken care of whether it has already appeared or it is appearing again. So Bhupen, if we remove that criteria of 40% and 20%, then I think your query will be resolved.
I mean, that 40-30 should be there actually, because that is for the generalization purpose actually, right? But on top of that, we can have this mechanism also, right? If the immediate neighbors is appearing, on second or third hop, right? They should have more weightage. So they can have some parameter beta or something. By that, we can, give them the more weightage.
Then in that case, we'll have to think of that weighted function. Na? We'll have to specifically design that weighted function, and more importantly, we need to have a mechanism of keeping track of direct neighbors as well as the indirect neighbors. So that means we'll have to keep track of the distance as well.
Yeah, that's true.
And if we
anyway, we are getting that details, right? We are capturing that hop 2 and 3.
Those detail will be there in the node features. That will come into the attribute in the part of node features. So if we are including the node features as well, we can do that.
Okay. Yeah. Thank you.
So I think is your query resolved?
Yeah. I mean, that's
okay.
Yeah.
Please.
We just need to discuss.
Okay. Rajat, is it clear for you?
Yes, sir.
Okay. Okay. We both were discussing. But as this has already been discussed, so this question will be leaved. So definitely now it cannot be. Okay. This question is already out. Okay. So we were discussing about GNN till now. Okay. So let's switch. Is it method that I can hide this? Is there any way? No. Okay. So next is GCN, graph convolution layers. It is one of the most popular baseline graph neural network model. We call it as GCN. It employs this symmetric normalized aggregation as well as self-loop updated approach. Okay, so the earlier message passing graph neural network was this, with the normalized value, with the self-loop. Okay, so GNN with self-loop plus normalized factor. Now, so GCN that define the message passing function as this. So again, I need not to repeat that this superscript is not the power. This superscript is the iteration. So some nonlinear function, learnable parameters WQ. So let me cover this. So V belongs to the neighborhood as well as the node itself. Okay, and node embedding. So sum of all the node embedding in the normalized form. Okay, so the only difference between this and this is that it is multiplied by some weighted matrix. Okay, so GCN is nothing. It is just the weighted uh, form of my GNN. So limitation of scaling issue. Why I have taken it? It demand huge memory space. Okay. Second, why I have specifically mentioned it revisit. Most probably the thing is, okay, I just want to ensure that you go through those 2 points, because but I have already explained those 2 points in full detail, so I don't think there's anything else to be, and anything special need to be extracted out from the same words. So means the main intention might be, okay, I just want to go through those 2 words. The next is the set aggregators or SAGE. So neighborhood normalization can be useful tool to improve the GNN performance, but we do more to improve the aggregate of operators. So is there perhaps something more sophisticated than summing up over the neighborhood embedding? So in spite of just summing up the value, do we have any other method? So we can take an average, okay, or we can have some form of product version. So that can be uh, a thing to be discussed, but it is again specific to the problem. So, but this summation can be applied in all the scenarios. So it is one of the method which is easy to apply, and it's applicable in almost all the scenarios. But the SAGE or the set aggregator is related to the sampling one. So the concept of sampling aims at selecting a partition of all the samples to represent the entire sampling distribution. Okay, fine. So the sampling algorithm on a large graph refers to the approach that uses the partial graph instead of the full graph to address the target problems. So either that sampling can be node-wise sampling, it can be a layer-wise sampling, or it can be a graph-wise sampling. So let us quickly look at each type. So node-wise sampling. So that lays a dominant role during the early stage of implementing GCN on a large graph. So there was a paper, graph sample and aggregator. Okay, so graph sampling and aggregator was the method, and the word that he had coined was graph sage. Okay, that paper is available. So Hamilton in 2017, and there was one more concept, variance reduction graph convolution network, VRGCN. It was suggested, not suggested, it was written by Chen in 2018. Okay, the inductive representation learning for a large graph sage. Okay, that's again widely being used paper. So you can go through that. So this was the node-wise sampling. The layer-wise sampling was suggested by different researchers, and they coined their own terms. So whatever the graph, SAGE, VR, GCN, these are the terms coined by the researchers only. Okay, so there is no example or there's no justification why he have taken graph, sample may say Acelia, aggregation may say G and E Helia. Why? No answer, because Hamilton can only answer it because he want a word sage. So sample aggregator, sample graph sample and aggregate. VRGCN, variance reduction graph convolution neural network. So that sounds good. He takes the first letter of each word, but he takes a different one. But that was his wish. Same is the case. Chen in 2018, the third paper in that year, he proposed an algorithm with the name Fast GCN. The full form was Fast Learning Graph Convolution Neural Network. Okay, so Fast GCN, Fast GCN. Why he missed learning, I have no idea. And Adaptive Sampling Graph Convolution Neural Network, again in 2003. So they come up with the second approach. They call it as layer wise sampling. So they propose to address the neighborhood expansion problems occurred during the node wise sampling. So when we will be studying about the node wise sampling, there will be one issue of neighborhood expansion. So in order to resolve that problem of neighborhood expansion, they come up with the different sampling method, and they call it as layer-wise sampling. Okay. Later, and these are the improvement. So first of all, they start with the node-wise sampling. 17, 18. They encounter, they identify some issues, they encounter some problems. So that then they come up with the next sampling method, layer-wise sampling. In the year 2018. Here also they encountered some issues. Then they moved to the graph-wise sampling. So it was in 2019 and 20. Okay, so these are the sampling methods are the improvements of the previous of the issues faced during the previous sampling method. So graph-wise sampling, they're designed to further improve the efficiency and scalability, such as cluster graph convolution network, cluster GCN, suggested by Chiang, and graph sampling based inductive learning method, graph saint. Okay, INT. Now why they take some intermediate word, I have no idea. They just want to have a word saint, so graph saint, and they coined their own algorithm as a graph saint. I should have highlighted bold. I should have made those alphabet bold. Okay, I will do it after this session. So these were three sampling method. We'll look at each method not in full detail, in just in a superficial way. So sampling paradigm. In a node-wise sampling, the node are sampled based on the target node of a graph. Okay, so if this is my target node, their neighborhood, who all based on the structural, based on the size, based on the reachability, some samples of node was selected. So that we call it as node-wise sampling. Some direct neighbors, some one hop, some one hop neighbors, some two hop neighbors, some three hop neighbors, and so on. Okay, based on some parameter, based on some logic that they suggested by themselves. Whereas in the layer-wise sampling method, the node was sampled based on the convolution layers of GNN model. Okay, so the same graph, if this is my graph, okay, so these are different layers of the same graph. Okay, different layers of the same graph means different set of vertices, or sorry, not set of vertices, a sub part of a graph taken at a time based on certain target node. Okay, whoever my target node is, based on their neighborhood, I'm taking various neighborhood at a time, and all those various neighborhood was called as the layers. Means parallel processing of node wise with a multiple selection of neighborhood. Okay, so one layer, some set of neighbors. In the second layer, second set of neighbors. In the third layer, a different set of neighbors. Not necessarily unique. There can be some common neighbors as well. So that was the layer-wise sampling method. Whereas for a graph-wise sampling, the subgraphs was sampled from the original graph and then used for the model inferences. Okay, so that means the graph was distributed, or we can say broken into some parts. Okay, some sample. So this is one sample, this is another sample. Okay, so multiple part of a graph, and each part was considered as one sample. So that they call it as graph-wise sampling. So heterogeneous graphs, I think heterogeneous graph means the graphs with multiple types of nodes, multiple types of edges, multiple types of connectivity. Okay, so heterogeneous graph have attracted more and more attention with regard to the rapid growth of data. Large graph not only include the millions of nodes, but also various data types. So how to train those GNN on a large graph has become a new domain of interest. So how to train it? So Lee et al. In the year 2019 proposed a GCN based anti-spam model. Okay, so GCN, graph based anti-spam. So he coined the word GAS model to detect a spams by considering both homogeneous and heterogeneous graph. So the paper title is this: spam review detection with a graph convolution network in the proceedings of 28th ACM International in the year 2019. Okay, so here whenever it is written A, B, or C, so that means this set of researchers have published multiple papers in the same year, and then they rank them on the basis of A, B, C, D. Okay, so whenever it is written as 2019 A, I think if you remember somewhere it was to C A, this is A, there was somewhere it is 2018 C. So that means those set of researchers, Chen et al. Means there were more than two authors of the same paper. Whenever there's an et al. In the name of the authors, which means this was the main author, and along with them there was few more, and the count was more than two. But all the group has published multiple papers in a same year, and we are referring to the third publication. Okay, so this is the meaning between that ABC, and this is the meaning of et al. Okay, right. So come back to the node sampling, graph sage. So graph sage can be viewed as an extension of the original GCN. The first extension is the generalized the aggregator function. So the embedding generation at a current I plus 1th depth from a target node V that belongs to the graph can be formulated as the use of LSTM aggregator and pooling aggregator to aggregate the information from the neighbors. So they use the LSTM and the pooling aggregator. The second extension is the graph sage applies the concatenation function to combine the information of the target node and the neighborhood instead of the summation. Okay, so there the aggregation in the aggregation function, they didn't sum the values from the neighborhood. They concatenate one after the another. So they use the concat function to get the updated information from the neighborhood. Okay? And this is the weighted matrix, and this will be the activation function, non-linear activation function. So for example, if this was the original graph and this was the target node, the node in brown, dark brown is the target node, So step 1 means sample the neighborhood of the target node. So these are the node at k equals to 1, means direct neighbors. These are the nodes which belongs to the hop distance 2. So this k equals to 1 and k equals to 2 is nothing. It is the hop. Okay. So from the hop, some set of neighbors are being used, sampled. So step 1, sample the neighborhood of the target nodes. Then step 2, aggregate the feature information from those neighbors. Utilize the aggregate function information to predict the graph context or the label, whatever the label will be. Okay, so if these are the nodes which are being selected as a samples, so and the information is aggregated from the leaf to node. Okay, so aggregation function, whatever the aggregation function, the method is, the information flows is always from the leaf to node. Okay, so we always start with the leaf node of that tree. So those green will aggregate the information to this one, and then those blue node will aggregate the information to the target node. Okay, and based on this, the information collected, they predict the context and the labels using the information which has been aggregated. So in order to make the GNN suitable for a large scale graph, graph says introduced the mini batch training strategy. So to reduce the computation cost during the training phase. Okay. So in each training iteration, only the nodes that are used by computing the representation in the batch are considered. Rest all were ignored, which significantly reduce the number of sampled nodes. Okay. So all the nodes will not participate in the computations. Only the nodes which are considered as a sample will participate. Okay. So that depends what should be your size of neighborhood. So in that case, the computation was reduced to a larger extent. How much time do I have? $39. Okay. So let me quickly. Can I have 5 more minutes? I just want to quickly finish this. If I have to start the attention network, then 62, and currently I'm at 50, 40, 50, 12 slides. I won't be able to cover. Okay, no issue. I'll stop over here. So I'll write stop at this point. Okay. So this is just for me to make a note where I have. So it's like a book note. So we'll start with the node sampling, but I should have finished this mini batch node sampling. 3 slides तो खत्म कर ही सकता हूँ. So just give me a minute. So I want to finish this 3 slides because I have introduced the concept of node-wise sampling. So let me finish this mini batch. So this is the visual comparison between the mini batch and the fixed size neighbors. So fixed size neighbors means if I have the s equals to 2, and when I say the mini batch of various neighbors. So layer 1 means I need to have sample node 9 and then sample 6 and then 1. Okay, so in that case, in the various layers, SAM family candidate, I can have a smaller set of samples. Okay, so in that case, my computation will be far less. Because I'll have to explain that fully, how to select those samples. Okay, so I'll stop over here. Should stop the recording.